For the last couple of lectures, we've been talking about the qualitative behavior of solutions of an autonomous system around an equilibrium point. Okay. Namely, we talked about stability of an equilibrium point, which was, qualitatively speaking, that an equilibrium point is said to be stable if solutions starting close to the equilibrium point stay for all times close to the same point. Okay, so that was roughly what stability was. We also talked about lack of stability, which we called instability. Okay, and also we mentioned a stronger version of stability, which we call asymptotic stability, in which the solutions not only stay close to the equilibrium point, given that they start close to the equilibrium point, but also they converge, they get closer and closer to the equilibrium point as time goes on. Okay, so those definitions are quite straightforward, very simple definitions, but they had one disadvantage. They were in terms of the solutions of the system. Okay, x that equals f of x. Therefore, in practice, that definition of stability, for instance, cannot be directly applied to a given situation. The reason being that, in general, we don't know how to obtain the solution of a nonlinear differential equation. Okay, so that's an inconvenience on the definition of stability, and motivated by that inconvenience, we searched for a method which would allow us to determine stability or asymptotic stability without actually requiring the explicit solutions of the system. Okay, and that led us to the most powerful method that we have in our disposal in theory of stability theory of dynamical systems, namely Lyapunov's theorem. And Lyapunov's theorem was, the idea there was quite simple. What we did, instead of solving or obtaining the solution of the system solution of the differential equation, we analyzed the behavior of a positive scalar function along the solutions of the system, okay, by looking at its time derivative. Okay, and if time derivative satisfies some definiteness properties, and then, like, if it's negative at all times, then we deduce that these solutions must stay close to the origin. Okay, so we saw that we can establish stability and asymptotic stability without actually solving the differential equation. Okay, so today we will remember those important concepts in a more precise fashion, and then we'll see a couple of examples on Lyapunov functions and in particular post definiteness of Lyapunov functions. Okay. So let's summarize last few lectures, important points. Okay, so we've been talking about the so-called autonomous system, x value equals f of x. Okay. X is a vector in Rn, which we call R state. So that makes f a mapping from Rn to Rn. Sometimes this is from a subset of Rn to another subset of Rn, but it doesn't, for the sake of simplicity, consider this case. Okay, f is from Rn to Rn. And then for this system, to be able to talk about a solution, first we need an initial condition. Okay, initial condition is where we start from. X t0 equals some point in space in Rn. Now, since this system is time invariant, without loss of generality, we can always take the starting time to be 0. Okay, and then the solution, starting from this given initial condition for this system, is a function of this type. Okay, again, this is not generally true, that is, a solution is not defined for all future times, but for the sake of simplicity, suppose that solution exists, it's unique, and it's defined for all future times. Okay, this is the time line to Rn. And in order for us to call this function, this mapping, to a solution, it has to satisfy two constraints. One of the constraints is the initial condition constraint, the other constraint is the differential equation constraint. Okay, namely, this, if it's a solution, should satisfy xt evaluated at t equals 0, must be whatever the initial condition is, and also it should satisfy differential equation du dt xt must equal f of x of t for all times. Okay, so that's our solution. And for this system, there's an important type of solution. Well, sometimes it doesn't exist, but supposing it does. And that particular solution, that important solution that we have been focused on, is the solution such that it takes the value which is its initial value for all future times. Okay, that is, it never moves away from where it starts. Such solutions or such points we call the equilibrium points for an autonomous system. Okay. So equilibrium is any point in Rn, called x bar, that satisfies the equation f of x bar equals 0 vector. Okay, so it satisfies that conditions. We call such a point an equilibrium point. Okay, in general, an anomalous system may have more than one equilibrium point. The famous example being the pendulum system. It may have no equilibrium points, or it may have infinitely many equilibrium points. Okay, and as we just said, the nice thing about equilibrium point is that if you start from that equilibrium point, then it means that you will stay at that equilibrium point for all future times, for all t greater than or equal to 0. Okay, and then we introduce the definition of stability for a given equilibrium point. Okay, stability of an equilibrium point. Okay, and even if x bar, the equilibrium point that we're interested in, is not the origin, we can always redefine our coordinate system. We can always slide things to the left, right, up, and down in appropriate for an appropriate amount, so that the origin coincides with the equilibrium point that we're interested in. So that means without loss of generality, okay, without loss of generality, we can always let the equilibrium point to be the origin. And the reason that we're letting the equilibrium point to be the origin is because the only reason is that it introduces some notational conveniences. Okay. Now, given an equilibrium point, well, from now on, that equilibrium point is the origin. The origin of, or the equilibrium point, the origin of this system x equals f of x is said to be stable if, okay, suppose this point is our origin, okay, and the board is our coordinate system, state space. Now, this equilibrium point is said to be stable if, for each epsilon you give me, I can always find a delta, okay, such that no matter what initial condition that we pick in this delta ball, okay, suppose that this is our x0, then this is x of t. For all future times, the solution never leaves the epsilon ball, and it should be the case no matter what epsilon you give me. You give me an epsilon I find a delta. Okay, epsilon 1, delta 1. You give me another epsilon, epsilon 2, I find a delta 2. If I can always find a delta, no matter what epsilon you give me, and this condition is satisfied as far as the solutions are concerned, then the origin is said to be a stable equilibrium point. Okay. For each epsilon, there exists a delta such that if we start in delta neighborhood of the origin, okay, norm of the initial condition, less than delta implies norm of solution for all future times is less than epsilon, okay, for all future times t. And now remember why we used, or we took the origin without homogeneity to be our equilibrium point. And I said it's because of convenient notational conveniences. If we didn't let x bar equal 0, but left x bar as an x bar, this would have become this, okay? Delta implies x of t minus x bar less than epsilon. But if x bar is 0, 0 vector, then this expression becomes a little bit short. Okay, that's the only reason that we're letting the equilibrium point to be the origin. Okay, now this is what we meant by stability, and we also talked about equilibrium point being unstable. It just means that if for some epsilon you can never find a delta and this condition is satisfied, and then such an equilibrium point is said to be unstable. And we introduced a stronger version of stability that we called asymptotic stability. Okay. Let's also remember that. An equilibrium point is said to be asymptotically stable if it's stable, and furthermore, all the solutions starting from an initial condition that's close enough to the origin converge to the origin. Okay. So this is the origin again. The epsilon delta definition or the condition must hold, and this time, along with staying within the epsilon ball, they should also converge as time goes on the solutions to the origin. If that's the case, then the origin is asymptotically stable. This is x0, let's say. Then this is x of t. The solutions converge to the origin, and then we have asymptotic stability. Okay, so asymptotic stability means to be stable, and x of t goes to 0 as time goes to infinity, at least for some delta. Now, as we mentioned earlier, these definitions, although they are very simple, easy to understand, they are in terms of the solution, okay, of the autonomous system. And we said in general, we don't know how to obtain the solution of a nonlinear system x is equal to f(x). And for that purpose, or motivated by that inconvenience, we introduced the notion of a Lyapunov function. Okay? Lyapunov function is a function that maps points from a subset of Rn, let's call it D, to the real line. Okay? And D has to satisfy some technical assumptions that are required for the proof. D is a subset of Rn. Okay, it's gotta be open, and it should contain, not surprisingly, R equivalent point inside. Now here, for such a function, we listed certain conditions. Okay, and one of those conditions were that v0 equals 0 and dx positive for all x in D minus, okay, except the origin. Okay, so this is, let's call it condition 1. And another condition that will be relevant is v dot of x is never positive for all x in D. Call this condition 2. And the next condition is a stronger version of condition 2, which is v dot x is strictly negative for all x, okay, except of course the origin. And here what we mean by v dot is the time derivative of the function v when a solution of the system x that equals f of x is passed through that mapping v of x. Okay? In other words, this was our system x that equals f of x, and for this system, okay, so we have to be given the system, otherwise, just with v, this v dot is undefined, is meaningless. But for a given system and a given function, the Lyapunov function, v dot is defined as v dot of x is the inner product of the gradient of the Lyapunov function, okay, with the right hand side of the system. Okay. And then we had the theorem, the Lyapunov's theorem, which stated that if conditions 1 and 2 hold, then the origin of the system x that equals f of x is stable. Okay. If 1 and stronger condition 3 hold, in that case the origin is not only stable but also asymptotically stable. The origin is asymptotically stable. Okay. So that was the important points in our last few lectures. Okay. Now let's briefly talk about, or try to visualize, what that v dot of x less than or equal to 0 or less than 0 means, and then we will talk about this property, okay, positive definiteness, in terms of some very special Lyapunov functions, namely quadratic Lyapunov functions. Okay. So what's the geometric meaning of v dot? V dot less than or equal to 0. Okay. So once again, v dot of x is the inner product of the gradient of V with the right hand side of the system, f of x, where f of x is x dot. Okay. So in other words, if this is the solution, x of t, okay, having started from somewhere and it's going toward wherever it should go, f dot, the meaning of f dot is the following. Suppose that we're somewhere here, at point eta, okay, and then it's somewhere on the solution. So at some time we're at eta, and next time, after a while, we're somewhere else, okay? In order to, so we're moving away from eta, okay? We're moving away, but in what direction, or what determines our direction of motion? This is the right-hand side, okay? Because x dot is the velocity of the solution or the state. So that means you evaluate this vector, f, at that point, eta, let's say, f of eta. And f of eta is also a vector, and that vector determines in what direction, at least for a while, you will be moving. So basically f of eta. And if you take that vector and put its tail to this point, eta, and draw it on the board like that, that means, first of all, it should always be tangent to that solution, and it's the direction of motion for a while, okay, at that point. Okay, now, let's combine this visual picture, okay, with v dot being negative, and for that, let's also draw or try to visualize what v of x is. Okay. One way to visualize v of x is as follows. Suppose that this is the origin, the equilibrium point that we're hoping to converge. And now choose the following sets. V of x equals some constant, some positive constant. V of x equals 1/2. V of x equals 1. V of x equals 7, and so on. Note that this is a positive definite function, so that means v of 0 is 0. So the set of points that satisfy v of 0 equals 0 is just 1. It's the original equilibrium point. But once you increase that number to something positive, v of x equals 1, and then it will be a family of points or set of points. Okay. The easiest way to visualize that is on the plane. You can take v of x to equal x1 squared plus x2 squared. Okay, so x1 squared plus x2 squared equals some positive number, gives you a circle whose radius is determined by the square root of the positive number. Okay, in general, it doesn't have to be circular. It could be elliptic, or it could be may have some very funny shape. We're not making any. We're not putting any constraints on the shape. The general theorem just says that it's a positive definite function. Okay. So then we have perhaps, and so on. Okay, so those are the level sets, so-called, of the autonomous function. Okay, the outermost ellipse, not ellipse, but the curve, let's call it, is, let's say, the set of points that satisfy v of x equals c1. And then we have this v of x equals c2, and then we have v of x equals c3, and so on. Okay. Now, as you now, since v is a continuous function, it's 0 at 0, it means that as you move along from the origin, as you move farther and farther away from the origin, this constant here, the right-hand side, must be larger and larger. So in this picture, C1 must be greater than C2, C2 must be greater than C3, and so on. Okay. C1, C2, C3. Okay, and these are level surfaces of x. Okay, now that's v of x, and if this is x2, this is x1, and then if you let this axis be v of x, that is, okay, x1, x2, and v of x. In that case, you can imagine that it's like a ball coming out of the board. And then you cut that ball with planes that are C1, C2, or C3, or whatever, away from the horizontal plane. And then when you cut that the cross section makes this curve. Okay, that's like an ellipse-looking curve, and then you project those curves onto the plane, and that gives you the level surface of so-called the optimal function. Okay, now pick a point x, let's say. Okay, this is x, and what's the meaning of the gradient of v at that point x? Okay, it means that in that direction, okay, the gradient, you're increasing in the fastest way. Okay, so the slope is highest, so that means this vector must be normal to the tangent plane on that particular point x. Okay. So this is tangent plane or tangent line, and that's that's the direction of the gradient. Okay, the steepest ascent. And then we have, so that's one of the vectors, and the other vector that we're taking inner product with is f of x. Now, if this vector and f of x, if the inner product, which is Rita, is negative, it means that the angle separation between this vector and that vector must be greater than 90 degrees. Okay. So that means if beta is negative, then f of x must be somewhere on the other side of that tangent plane. Okay. So this is our f of x. The angle is greater than 90 degrees, therefore beta is negative, and that picture immediately tells us what's going on. If it's always negative, so that means at any point the solution, note that this f of x is the instantaneous velocity of the solution. So at any time, the solution is always pointing to the inside of the given level set. So, okay? So that means you're going inside, so you will be landing on some other level set that's inside the larger level set, and from that level set you move to a smaller level set. From that level set you move further to the smaller level set, and that means this C becomes smaller and smaller as you move along the solutions. Okay, and this C becoming smaller and smaller, that means v of x becoming more and more equal to 0, and since it's 0, it's continuous, so that means x must be converging to the origin. Okay, so that's the very simple geometric meaning behind that condition, v that is less than 0. Okay, so let's write that down. So this inner product less than 0 means that the angle between vectors the gradient and the right hand side f of x is greater than 90 degrees. That implies, okay, which is particularly easy to see on that picture. That implies f of x is pointing the interior of the surface. V of x equals some positive constant. Therefore, once the solution or the trajectory enters the region V of x less or equal to c, since the derivative is never positive, it can never leave. So that's the pictorial explanation, sort of Lyapunov's theorem, which makes use of a Lyapunov function, and that function has to be positive definite. Okay. Now we'll talk a little bit about positive definiteness and how it can be checked for a very special type of Lyapunov functions, namely quadratic function. A Lyapunov function candidate should satisfy x positive for x different than the equilibrium point, and it must be 0 at the equilibrium. Okay, v0 equals 0. Such functions are called positive definite. Okay. Therefore, we can now re-express Lyapunov's theorem in a more compact way, in a very short way. Equilibrium, the origin is asymptotically stable if there exists a positive definite function whose time derivative is negative definite or negative semi-definite. And negative definiteness and negative semi-definiteness are more or less clear what they mean, but we're going to give the definitions anyway. Okay, and here goes definition. A scalar function v from d to r. It is a subset of Rn. If this d bothers you, you can take it to be Rn to complete space. Okay, it's not that important. With v 0 equals 0 is set to be positive definite if Vx positive or x different than the origin. The weaker version is called positive semi-definite. Positive definite if v of x is never negative, okay? So it's positive, but sometimes it's also 0 at points other than the origin, okay? So that's positive semi-definite. Clearly, if a positive definite function automatically satisfies that condition, that for positive definite function is also positive semi-definite. And we have the other direction. It's called negative definite or negative semi-definite. If minus v of x is positive definite or positive semi-definite. Okay. Then if it's neither of those, then such a function is called indefinite. Okay. It's called indefinite if neither of them. Okay. Now, it's not straightforward for a given, for an arbitrary function, arbitrary scalar function. It's not straightforward to check, to see, to prove that whether it's positive definite or negative definite or not. Okay. But there is, so what I mean by that is there's not a general rule. Okay. That when you apply it, you can automatically see that whether it's positive definite or not, or it's indefinite or negative semi-definite, things like that. There are, however, nice rules, okay, easy to check if the function that you're working with is a very special type of Lyapunov function candidate, namely quadratic functions. And usually they're always our first attempt. If you want to show stability or reversibility of an equilibrium point, usually we try our chances with a quadratic function, okay, because it's easier. It's much easier to work with them, but the only problem is that they don't generally work, okay, but it's okay. It's doesn't cost much, okay, time-wise, to check, to see whether they will work or not. Therefore, we always try quadratic candidate first. Okay. So, it is therefore worthwhile to say a few things about quadratic scalar functions, quadratic Lyapunov function candidates. Okay. Here goes the definition. A quadratic function V from Rn to R is such that it can be written as a summation of only second order terms. Okay, so if we have, this is the space Rx, so x is x1, x2 up to xn. So the terms will be the terms of v of x will be like x1 squared, x2 squared, x1, x2, x3, x5, those products, and so on. And if when that's the case, you can always express such a quadratic function in terms of a symmetric matrix, symmetric real matrix. And then, once you have a symmetric real matrix, you can check definiteness, positive definiteness, negative definiteness, or semi-definiteness by directly over that matrix, okay, by looking at its eigenvalues or something else. Yeah, it can be written as v of x equals x transpose p of x, where p is an n by n real matrix. And without loss of generality, we can always take it to be symmetric, by which we mean that its transpose equals itself. We say the matrix P is positive definite or positive semi-definite, and write P greater than 0 when we mean P is positive definite, or P greater than or equal to 0 when we mean that P is positive semi-definite. When in fact we're talking about the positive definiteness or positive semi-definiteness of the mapping, defined as X2 X transpose PX is positive semi-definite. And that definition can easily be extended to the negative domain. That is, P is said to be negative definite or negative semi-definite, and we write P less than 0 to indicate that, or P less than or equal to 0 to mean that P is negative semi-definite when minus P is positive definite or positive semi-definite. Then, the important question, which has a very nice answer, nice and simple answer, is that given a quadratic function, which is our, let's say, Lyapunov function candidate, how can we check its definiteness, whether it's positive definite, negative definite, or negative semi-definite, and so on. For that, we can use the following fact. All we have to do, it turns out, that is to check the eigenvalues of P matrix. If all the eigenvalues are positive, first of all the eigenvalues must be real, because P is real and it's symmetric. And then, by looking at the sign of the eigenvalues, we can directly say whether P is positive definite, negative definite, indefinite, negative semi-definite, and things like that. Okay. Here is the fact that we will use, but not true. Given the symmetric matrix, P is positive definite if and only if all eigenvalues of P, let's note that by lambda I, satisfy lambda I positive. And P is positive semi-definite if all the eigenvalues are non-negative, okay, greater or equal to 0. Moreover, P is positive definite. Here's another check. If all the leading principal minors, what they are, I will define soon. Leading principal minors of P are positive. Now, in the notes, in the lecture notes, this statement is extended to the semi-definite case also, that it's said that P P is positive semi-definite if all the leading principal minors of P are non-negative. Okay, so that's an error, so that's wrong, it's not true. Okay, so this statement is only true for the positive definiteness case, it doesn't extend to positive semi-definiteness case. So this is in the notes, the error. Okay, so you may want to correct that. So let's erase. Okay, now what are leading principal minors of a matrix? Leading minors. So suppose this is our matrix 3 by 3. A, B, C, D, E, F, G, H, I. By leading principal minors, meaning the following determinants. Determinant of this 1 by 1 matrix, then determinant of this 2 by 2 matrix, and then determinant of this 3 by 3 matrix, which is the matrix itself in this case. Okay, so you go all the way to the end and you compute if when the matrix is n by n, so that means it will have n leading principal minors. So n determinants, all those determinants must be positive. Okay, for a symmetric matrix, if that matrix is to be positive definite. Okay. In that case, in this case, leading principal minors are determinant of this 1 by 1 matrix. A is A. Then we're talking about determinant of A, B, D, E matrix. A, B, D, E. And finally, the determinant of the entire matrix A. Okay, so let's see a very simple example for the leading or the positive, checking positive definiteness through leading principal minors. And then in the next lecture we will continue with some other examples. Example. Suppose that the following function is for some system R Lyapunov function candidate, therefore it has to satisfy positive definiteness. Okay. And it's quadratic and it has the following form. V of x equals, where x is in R3, is x transpose, which is this row vector x1, x2, x3 times p times x. Okay, and the P matrix has the following entries: A, 0, 0, 1, 2, 1, 2, A. And A is, let's say, some design parameter. We're designing a Lyapunov function. Okay, let's call this matrix P. Therefore, V of x has the following from x transpose px. This is being x. This is our vector x. And now, if this is to be a Lyapunov function candidate, P has to be positive definite. Okay. So let's determine positive definiteness or conditional positive definiteness of P in terms of the design parameter A. And for that, we can apply this test, that is checking the leading principal minors. Okay. Leading principal minors of P are, okay, this determinant is A, and then we have this determinant, it's A squared minus 0, so it's A squared. And finally we have the determinant of P itself, which is A cubed minus, okay, A cubed plus 0 plus 0, then minus A minus 4A minus 0. So it's a squared, a cubed minus 5a. So that's the determinant of p. And for p to be positive definite, we require all these three numbers to be positive. Okay, so a should be positive, a squared then automatically is positive, and then furthermore we should have a cubed minus 5a to be positive. Okay, so for p to be positive definite, we need a positive, a squared positive, and a times a squared minus 5 positive. Okay, so a positive, then automatically a squared is positive. If a positive, then this positive means that this thing must be positive and this thing must be positive, means that a square must be larger than 5. And since a is positive, that means a must be larger than square root of 5. And that's the intersection of all these conditions. Hence, for a larger than square root of 5, u of x is a positive definite function.